Welcome for you chemistry students. So we've been looking at rate of reaction, and so far we've looked at different factors that can speed up a reaction or slow it down, things like changing the temperature, changing the concentration, the pressure, the surface area, etc. So today we're going to look at a chemical, like a formula, an equation that quantitatively describes the rate of a reaction, and it really focuses on concentration of your reactants that you've put in, because that has a really huge impact on the rate. So every reaction is very specific, like on what day you did it, what the temperature in the room was, what the air pressure was if you're involving gases. So when we do this rate law equation, which is right here, we have to base that equation on the experiment data that we get from doing that reaction. And it's going to be different from one day to the next. So every single reaction is going to have its own little rate law that could vary literally from one day to the next. All right, so R is rate, okay, and I've put here it's in moles per liter per second. That is pretty standard. It's not set in stone. Usually we're looking at changing concentration over time. The time could be minutes. Sometimes we might just look at moles over time. Like if it's not in solution, it doesn't have to be moles per liter. Okay. X and Y are two reactants, and they are definitely going to be concentrations. Okay, so moles per liter. Now, K is a constant, and we will look at eventually how to figure out that constant. And what we're really interested in is this thing called M and N. And these are exponents that you raise the concentrations to, and quantitatively they tell you what effect changing the concentration has on the rate of the reaction. All right, so I think we've basically gone through most of this. I should point out that K can have some weird units. That is one thing for sure, depending on the reaction. And something you might just want to jot here is K, the constant for that reaction, is going to take into effect things like the temperature, the pressure that day, the surface area, if you had solid ingredients, where, was it ground up or was it not? Okay, so figuring out these values of M and N, or the exponents that you're raising the concentrations of the reactants to. I think the videos that you have watched by Professor Dave and Bozeman Science did a really nice job of showing some examples of where these come from, but I did just want to summarize it here for you. So essentially, when you're wondering what the concentration of a reactant is going to do to a reaction, you need to change it. So you change the concentration of your reactant, and then you measure the rate of the reaction to see what effect there is. If there's no effect at all, it's called zero order. So, you have a little or you have a lot of that reactant, and your reaction proceeds at the exact same time. So you're measuring concentration change, or measuring volume of gas produced, or looking at the color change as a precipitate is made using a photospectrometer, and nothing changes with your rate. So that is zero order. Anytime you raise something to the exponent 0, it just equals 1. So it essentially cancels out that concentration as having any effect. The second scenario is you do something to a reactant's concentration, so you double it, and your rate goes twice as fast, so it doubles. Or perhaps you triple the concentration and your rate goes 3 times as fast. That is a first order reaction. And finally, if you change your concentration and then what you find is that your rate really speeds up, like for example, you double the concentration and the rate goes 4 times as fast, or you triple it and now the rate goes 9 times as fast, then really what's happened is the rate is increasing by a square of what you've changed your concentration by. So that is second order. There are third order reactions, but we're not going to be doing those in this course, and they're fairly rare, so you don't need to worry about it. All right, so the best way to understand this is to do an actual problem. So this is a set of data that someone's done in a lab where they've done an experiment 3 different times, so 3 trials, and they have recorded their initial concentration of both reactants and then measured the rate of the reaction proceeding. So you'll notice that sometimes these 2 concentrations didn't change in A, but here they changed in B. That is very important because you don't want to change 2 things at the same time, because then you won't know which one is causing the effect. Similarly, here B is the same, 0.18, but you'll see that A was changed. So what is very key in solving for your exponents, m and n values, is that you pick pairs of data to analyze where only one of your reactants is changing. So, for instance, if we were going to start by analyzing A, so reactant A, I could look and see, well, first of all, I want to change A. I don't want to do 1 and 2 because that's not going to tell me anything. I want to do either 1 and 3 or 2 and 3, but I can't do either of them because I have to look at B and realize that I don't want B to be changing at the same time. So if I look and see that B is exactly the same in trials 1 and 3, it's 0.18, but I have done something to A, then that's a good choice because that effect on the rate is going to be due to A. Now, I like the way this question, the numbers aren't quite as tidy as they were in the videos you watched. Those videos were great, but you could probably do the math in your head. And I wanted to give you a question where you might actually have to get your calculator out possibly to figure out what the actual change was. So we are going to use trials 1 and 3. And obviously you would not have to write this down going forward all the time. I just want you to have a reference note. And you need to see, okay, well, what did we actually do to the concentration? Okay, so for concentration of A, take your bigger number and divide by the smaller number. Do not worry about units because we're only looking for a ratio here. Now, if you did it upside down and did 0.36 divided by 0.72, you'd get a half, and it's not that the math is impossible, but it's not as nice, that's for sure. So basically this is telling us that concentration of A was doubled. Okay. So now we want to see, well, what was the effect on the rate? So for rate of A, we have to use the corresponding numbers. So we did 0.720 on top. So we go over here, 0.470 on top, and then we go across 0.117. And when you divide that, you'll get 4. So the rate quadrupled. And if it quadrupled, that is like the square of what you did to the actual concentration. So 2 squared equals 4, and it's that square that is now going to tell you that A is second order. Okay, so that's our first piece of information. So what that means is A in our equation is going to be raised to the power of 2, but we'll put the whole equation together in a second. Okay, so now we're going to do B the same way. And for B, again, we want to change, so it's either got to be 1 and 2 or 2 and 3. And of course, the obvious choice is 1 and 2 because A did not change. So we're going to use number 1 and 2. And we're going to take the big number, divide by the small number. So we want 0.720 divided by 0.180. And when we get that, we get 4. Okay. So we quadrupled the rate, or sorry, the concentrations, sorry. Okay, so B was quadrupled. Okay, so now we're going to look at the rate for B. And you need to choose the same numbers. So we had, we said 1 and 2, so we did 0.70, so we need 1.880, and we're going to divide by 0.470. And when you do that, you get 4. So rate quadrupled. So we did exactly the same. We increased the concentration by 4 times, and the rate went 4 times as fast. So therefore, B is first order, or B will be raised to the 1. Okay, so now let's put this all together and write the rate law equation. So R equals K, which we'll solve later, times A, which we said needs to be raised to the 2 because it's second order, and B is going to be raised to the 1. So that is what we were sometimes just solving in our head with some easier examples, which is fine. Okay, so every reaction has an overall order, and it kind of depends on how many, different reactants there are. If there's only one, then your overall order will just be whatever order that reactant is. But essentially, you are just going to add up your values. So it's going to be M plus N, 2 plus 1, which is 3. So we say it's third order overall. Okay. Now we can solve for the value of K quite easily simply by looking at any of the trials. So we could use trial 1, we could use trial 2, or we could use trial 3. It doesn't matter. So I'm just going to use trial 1 because it's the first one. And we're just going to plug everything in. Okay, so for trial 1. Now, if we're solving for K, we're going to have to rearrange this equation. So we're going to want to get rid of all this, and it's currently being multiplied, so we're going to divide it out. So K is going to equal the rate divided by A squared B raised to the 1. Okay, so from trial 1, plug in all the numbers. So the rate in trial 1 is 0.470, and I am going to put units now because I want to show you what happens with the units because some weird stuff goes on. Okay, and then we're going to have 0.720 moles per liter, and that is going to be squared. And then we're going to multiply by 0.180 moles per liter, which is just raised to the 1. You can write it if you like, but it's just going to, it's not going to have any effect whatsoever. Now, I think I'll just rewrite this one more time. I know we're getting a little tight for room, but I just want to show you what happens with this. So we still have this on the top, moles per liter per second. And here When you square this, because you're going to have to square it, you're going to have 0.518. But look at the units. It's going to be moles squared over liters squared. Okay? And then that is still going to be multiplied by 0.18 moles per liter. Okay, so you should practice doing this because the math is kind of crazy. And if you solve it correctly, K is going to come out to equal 5.04. But let's look at what happens with the units. So we've got moles per liter times seconds, and then a moles per liter here. So that whole mole per liter and that whole mole per liter can cancel out. So then we're left with a 1 over seconds over top of mole squared, liter squared. And if you think back from math, if you have a fraction over a fraction, you invert and multiply. So what you'll end up with is liter squared per mole squared seconds. And that weird unit for the constant is necessary to make all these other units cancel out so that we end up with rate in moles per liter per second, because that was what rate should be measured in. So the unit for K changes depending on whether it's a first order, second order, zero order reaction. You'll get different units. Okay, so now that we know that, we could, if I could just make some room here, we could actually put this whole thing together and say rate is equal to 5.04 liters squared, mole squared seconds, all times, oops, I don't want a round bracket there, all times A, whatever concentration you have, you would plug in, B, whatever you have, you'd plug in, and this is your totally complete rate law equation for that reaction on that day. Okay, so the A to the 2 and the B to the 1 will be consistent. It's this K value that could change a little bit day to day. Okay, that is it for today. Thank you for tuning in once again.